Well, thank you all for joining us this afternoon. We're here with Kylee Branning, who is a PhD student at the University of Alaska, working on her degree in space physics. She's here to talk to us about Aurora, what it is, how it's formed, the color changes, how to study it, the different techniques used to study the phenomena. And her specialty is something called thermospheric wind speeds, if I get that right, which
Yep.
I could talk about that too, but everything I said I'd make up because I have no idea what it is. But this is all in conjunction with the 75th anniversary of the Astronomical League. We've been around since 1946. We started out with a few thousand members, but now we're way up to over 18,000. So during the year, we're putting together a number of programs to show all the different aspects of astronomy, and this is but one of them. Kylee she got her undergraduate degree from the University of, Northern Michigan University in Marquette, Michigan. And that's where she first saw Aurora and became really intrigued by it and continued her education by studying the phenomena. So I'd like to turn it over to Kylee now, and she can tell us what she knows about this phenomena and how cool it really is.
Yep.
Kylee?
So I think I'll just screen share if possible.
In a moment.
Okay.
There you go. Anytime.
All right. Give me a second to pick the right screens to share. Whoops. Let's not start in the middle of the presentation. Let's start at the beginning.
Looks good.
Okay. Still look good?
Yes, it does.
Awesome. Okay. So I'm going to talk about the Aurora, obviously. I've been doing this for, since 2015 was my first presentation. And so hopefully I know what I'm talking about since it's been quite a while. But we're just going to start with a little bit of a background. So this is Earth, and we have a 6,700 kilometer radius at Earth. And then around us, we have this gaseous envelope that separates us from space. So within that, we have this 15-kilometer altitude range where all human activity takes place. So any air traffic or anything is going to occur in this range. And then above that, we have what's called the neutral atmosphere. And this is just an envelope around us where the atmosphere is thinning, we're getting out towards space, but technically it's still our atmosphere. And that goes up to 100 kilometers altitude, depending on who you ask. I'm not going to argue that, but many people will. Outside of that, we have what's called plasma, and we are a 99.999% plasma universe for the known universe. And technically, only 4% of the universe is actually known. The rest of it is what we call dark matter and dark energy. That's a different story. I don't know much about that, so we're just going to move on. We're talking about plasma here. So on Earth, where can we see plasma? Neon lights, obviously, also fluorescent lights. That's when plasma glows because it's conducting electricity. One of our only naturally occurring plasmas is lightning. So that's pretty cool because usually on this planet, it's too cold for plasmas to occur naturally. Further, we can also create plasma in a laboratory environment. It's really expensive, so we usually don't do that. And everyone's favorite kind of plasma, the plasma screen TV, naturally. So now that we know a little bit about plasma, let's talk about more Aurora-related things. So where does the Aurora come from is actually a misleading question because we should actually say, where does Earth's Aurora come from? Other planets do have Aurora, so one example of that is Jupiter. Jupiter's Aurora does not come from the sun, typically. It actually comes from its volcanic moon Io, or Io, depending on who you ask again. So that moon is constantly erupting sulfur and oxygen, which then interacts with Jupiter's atmosphere and creates its own aurora. And in this image, if I get my little laser pointer out real quick, you can actually see the moon and the trail from the moon as it moves around the planet. So pretty cool out on Jupiter there. But we're talking about Earth because that's where we are. That's what we care about in this presentation. So where does the Earth's aurora come from? the sun. It's just an enormous power plant for us, specifically down at the core of the sun. So the core of the sun is very hot, and down there we have a little hydrogen gas at the core that's eventually going to get squeezed together under all of the pressure that's down there, and it creates a helium atom. This is called nuclear fusion. And when that happens, all that pressure on the the hydrogen gas is then creating the helium atom. But then when that happens, it releases energy as well. So some of the mass is converted into energy in the form of light. How does that get out of the sun though? Well, it moves up from the core through the radiation zone into what's called the convection zone. So this hot inner plasma is rising, that energy is coming up and out, and then when it gets to the surface, it cools back down, and that causes the plasma to sink again. So once it sinks, then it gets heated again, and it rises, and we get these little convection cells. So that's just these little circles that are where the plasma is just rotating around. And once this happens, we've got charged particles that are moving around. And when that happens, anytime that happens, we'll get a current and magnetic field created. So that's all great, but how does this get to Earth? Solar wind. I'm sure you've all probably heard about the solar wind, so we're just gonna talk about some brief signatures of it. So it's a stream of charged particles or plasma coming from the sun. Now, these numbers can vary a lot. So if the solar wind, if the sun's being calm, solar wind can actually go down to like 200 kilometers per second velocities. And if it's crazy, it can get up to 1,000 kilometers per second. But these are more kind of average numbers around, we usually say 450 kilometers per second. It's very hot and it takes a few days to reach the planet. In a few ways, it does leave the sun and reach the planet. One of the most interesting and simple ways is a coronal mass ejection, or as I like to call it, a sun burp, which is basically just an explosion on the surface of the sun that flings this stuff at us. So sometimes, like in this image, it actually isn't coming at Earth. So this instrument here, this little white line is the outside of the sun. And then we have this, little filter here so that we don't hurt our instrument because the sun's very bright. And this CME is not coming at us because, this instrument's in between us and the sun. So what does it look like if it is coming at us? Well, here we have an image, a movie from this instrument, and as you'll see, it'll be very obvious when we do see a coronal mass ejection coming towards Earth. And one thing to point out is that that white line is the radius of the sun, or the outside of the sun, and the sun's diameter is 109 times bigger than Earth. So that's what this detector looks like when we do see these events coming at Earth. We get all these little spots on the detector, and that's how we know, hey, maybe we'll have some interesting aurora in the next day or so. So, as I said, that's now traveling towards Earth, but let's assume for a second there's nothing in the atmosphere and Earth is just alone. So that's when Earth's magnetic field looks like this cute little dipole, just like a little bar magnet. We have our little magnetic field just hanging out, looking all symmetrical. But of course, the sun's got to mess that up with its own little magnetic field. We call that the interplanetary magnetic field. And it's basically like someone with long hair in a wind tunnel. It just gets blown backwards. So this is our actual shape of our magnetic field. You can see that we have this tail region, which is caused by the interplanetary magnetic field pushing on our regular dipole field. So a few things to note in this. We have what's called the bow shock, which is created just like those supersonic planes. Our interplanetary magnetic field is moving at supersonic speed, creating this little bow shock for us. This is what protects us from the sun. And not all planets have this. So Mars actually does not have a dynamic magnetic field. So Mars is just constantly bombarded with sun particles and stuff, which is kind of cool. Just a little side note. So now we're going to focus on this interplanetary magnetic field, and looks kind of like, Earth's magnetic field. But the interesting thing about the interplanetary magnetic field is it can have two different orientations. So this is a northward interplanetary magnetic field. I call it the boring one, so we're not going to talk about it because nothing super exciting happens there. The one we care about is the southward pointing magnetic field. And what's interesting about this is when we get what's called reconnection. So whenever we have two opposing directions in a magnetic field, we can have a reconnection event. And that looks something like this. So we have a northward pointing magnetic field and a southward pointing magnetic field coming together, reconnecting, and shooting off in different directions. So to demonstrate that, we have that point where there's opposite pointing magnetic fields. They connect, and now remember, this magnetic field from the sun is carrying with it all those particles from that CME event, and those are going to shoot down into the Earth's atmosphere. And when that happens, those charged particles move down to the surface, and we get daytime aurora. Now, daytime aurora is kind of hard to see, so that's why we don't really talk about it too much, because the sun's obviously bright, so you can't really see the colors too much. Sometimes you can if it's super strong and it's kind of like on the cusp of night, but it is there. It does happen. The more interesting one, though, is the nighttime aurora. So as you can see back here, we also have a point where there's two opposing directions of the magnetic field. So again, we're going to have that reconnection event. That's going to shoot those space particles back towards Earth. And when that happens, we get our general nighttime aurora. Now, if that was all confusing and fast, here's a nice little video from NASA that also shows it, and it shows it in 3D because, you know, space is 3D and not 2D. I just am not that talented with modeling it. So again, here's the sun. Sun's gonna shoot off some particles towards Earth. We're gonna get that reconnection event, moving those particles to the tail region. That's gonna squish that tail region down together, as you can see there. And then those field lines are gonna combine and snap off like a little rubber band, shooting particles back to Earth. And there we go. Now we have our beautiful aurora. So as we're in the northern hemisphere, we usually know about the Aurora Borealis, but if you paid attention, then you saw that those particles snap in the directions of the northern and southern hemispheres. So we also have what's called the Aurora Australis. So here are two auroral ovals, as we call them. And the cool thing about these is that the aurora is conjugate, which means if you put a camera in the same location in the northern and southern hemisphere, you'll see the same things happening. And there's a few examples of this online, and I strongly encourage you to Google Conjugate Aurora. Unfortunately, we don't have too much time to get into it. It's very complicated, but also very cool to see. So Conjugate Aurora is what that's called. So that's cool and all, but where does the light in the aurora come from? So now we're going to talk about this guy. We're going to call him Oxygen Atom, and he's just hanging out in our atmosphere, chilling, not much going on. And then, as we talked about, those charged particles are coming down from space. So that's what we're going to call this little guy. Let's say he's an electron. And when those come down from space, they come into our atmosphere and collide with our atoms in the atmosphere. I like to kind of think of it as, you know, kind of getting punched in the face. So someone comes at you, punches you in the face, what happens? You get excited. You kind of go, whoa, what the heck? And you jump up to a higher energy level. And then you kind of hang out there for a while, like, what just happened? But eventually you calm back down, you know, settle down again, go back down to that lower energy level. And when you do that, you kind of wipe the sweat off, right? Well, that wiping the sweat off is emitting a light photon in this case. So, and that's exactly what happens. Those electrons come in from space, collide with the atoms in the atmosphere. They jump up to a higher energy level. Eventually, they want to go back to where they started. So they let off that light photon, and that is how we see the aurora. So here's how we get the different colors of the aurora. So this is actually quite interesting because oxygen can actually create the red aurora up at 300 kilometers altitude and the green aurora that occurs lower down at 150 to 100 kilometers altitude. That's because up high in the 300 kilometer altitude region, there's a lot less stuff. So there's a lot less collisions going on. They're not getting that excited. It's a different energy level. Whereas when you get the strong penetration from the solar wind, we see this green oxygen, which is colliding multiple times and just happening at a different energy level. Also, we can see red aurora down below 100 kilometers altitude, and that's from nitrogen. And we can also see blue, but it's less common. Cool, though. So that's our general colors of the aurora. This is our spectrum of these lines of the different colors we can see. And that's pretty much how the colors are created. I'm going to skip these real quick. So now how can we study this? There's multiple ways. As I said before, you can create a large chamber and create your own plasma, or you can build and fly a spacecraft. We can also do it from the ground. So we can take cameras from the ground, point them up to the sky, and watch the aurora, measure different things going on, or you can just model it. Now, each of these have their drawbacks. Obviously, the lab and flying a spacecraft costs a lot of money. Cameras on the ground, less expensive. And if you want to just model it, then here I am. You find a grad student. So at UAF, we do a lot of these. We actually do a lot of aurora research. One of our most common things is SuperDarn. SuperDarn is a high-frequency radar that measures plasma motions. So the cool thing about that is it's global, so you can find SuperDarn all over the place. And it's pretty sweet because then you can combine data from everywhere and kind of get a full picture of what's going on. We also do numerical simulations, which is sitting in an office, typing away at a computer, using some data and simulating what's going on. And one of the things that one of our faculty members here studies is magnetic turbulence with that. The thing I like the most, which is what I do, is ground-based optics. So using a camera, pointing it up at the sky, we can actually measure color changes in the aurora. And then with the color change, it gives us a Doppler shift. So it's the same thing as the car horn going by, you know, it's loud, or it's higher pitched and then lower pitched. As the color changes, if it's higher pitched or lower pitched, we can tell if it's moving towards or away from us. And that's how we tell the wind speeds. So that's what I do. Sorry, went a little too long on that one. But we can also use a few other instruments to measure different things, wave frequencies, and we also study how the aurora can affect communications because it is charged and it can affect satellites and things like that. And then one of the coolest things about UAF is that we are the only university to own a rocket launch facility, which is Poker Flat Research Range. So here's a few images of that. These are SuperDarn radars, some modeling simulations. This is from our ground-based optics where we measured color changes and then got wind speeds from that. And this is down in Antarctica. This is our infrasound. So now you guys get to watch a beautiful Allsky camera image. So pay attention to that. Out at Poker Flat, we have lots of cameras looking at the sky, measuring different things. These are just some examples. This is a particularly interesting night because I believe it has a lot of red aurora, which is quite rare to see, but very sweet. You can see it's quite active night. One of the interesting things about these cameras, though, is our orientation. So you can see north is actually at the bottom of this image. And the way we did that is if you're facing north and you look up, then technically north is at the bottom of your field of view. And that's how we orient our cameras. I'll just let that play because it's pretty. Poker Flat's a very interesting place too because we can also do sounding rocket missions. And with those, we can launch rockets into the aurora. So we watch our cameras and watch our ground-based data and pick the perfect time to launch the rocket so that we catch the perfect structures of the aurora or whatever we're looking for. And then we launch a rocket up into it, and we can do things like chemical releases so that the chemicals will flow with the winds or the charged particles, depending on what we want. And those are really cool because they can create clouds in the sky. that are actually visible in these cameras, not on this night in particular, but I'll show a few examples of that. So also in Alaska, this is what a rocket looks like just before it launches, which is quite funny. We have to encase it in styrofoam, otherwise the electronics don't work. So we can encase it in styrofoam, send heat to it and keep it warm until we're ready to go. And then we just blow it up with the styrofoam on it. So if you go out to the rocket launch facility, you can usually take home a little souvenir of burnt styrofoam, which is always fun. So these are those chemical releases I was talking about. So this is from a mission called Super Soaker, which is quite funny. They were trying to create clouds. So what they did was they launched a rocket with a barrel of water and they blew it up. So that's why they called it Super Soaker. And this here is called trimethyl aluminum. And what that will do is it burns on contact with oxygen, and we just take images of it, we align it with the background stars, and then we can tell which way the winds are blowing up at those high altitudes. And it's tricky because it's the transition region between space and Earth's atmosphere. So there's no other way really that we can get those measurements. It's just kind of gotta launch a rocket. Here's another example. So this is the Azure Rocket launch out in Norway. So this one's a little different because instead of just releasing a trail of chemicals along that line, we actually shot canisters out the side of the rocket, and these will move in different directions. So those little purple ones you see here, those are moving with charged particles, and the other colors are moving with the background neutral winds. And you can see that. So if we go in between these two, you can see those purple ones moving off to the right there. Another cool thing we can do is UAF owns the Harp Facility, which is a high frequency active auroral research program. I had to think about that one for a second. So it's basically just an array of giant antennas. But what we can do is we can modify the ionosphere and create our own fake aurora. And I've actually done this for my research. So here's a few data outputs. So these are like those Allsky cameras. This is just looking straight up from the Harp Facility. You can see this little blob here. That's where we excited the atmosphere above those radio antennas and created our own fake aurora. And then we can take measurements of that and see what the winds are doing that way. And we can kind of control where it's at, but not really, but it's pretty fun. Another thing we have is this giant green beam that looks alien-like. That is our LiDAR facility. So that it's laser radar. So it shoots light into the sky and then it waits until there's something to interact with. And then it reflects back down and we can tell lots of different things from that. So, densities and if there's clouds, but we usually don't need to know that. We have cameras for that. So pretty cool though. I'm gonna jump back to these slides. The last thing I wanted to give you guys was a few resources. So let me know if you can see that. Cool. So this is our Allsky camera. This is very cool if you want to see footage of the aurora. So it's just a YouTube channel. You can go through, you can click on any night, and it'll play you a video of what the aurora did that night. Might take a second, but it's pretty neat, and it runs often. I also have a link to give you guys so that you can view it live if you want to, if you don't already know about that. I might have picked a not so interesting night, but basically you can just view the aurora, watch what it's doing. Pretty cool, just like that video I showed you. Another neat thing though is if you go back in our archives of this, you can actually view these on your phone and view them in 360 degrees. So you basically hold your phone up to your face and you look around and you'll basically be looking at our sky as we're seeing it. And that's pretty fun to do. There's a lot of active nights. You can usually tell the active nights, you know, something like this would probably be interesting. You can see an arc there in that video as well. So definitely recommend you go check these out. If you want to watch in real time, you just go to allsky.gi.alaska.edu, and that will take you to our live camera. It only runs when it's dark out, because there's no point in us showing you the sun. You can see that from your house as well. So, but for our Aurora, you can check in at nighttime here. Maybe if you're up early, since we're in different time zones, then you can see the Aurora in the morning. Definitely recommend checking that out. If you want to get fancy, you can go view real-time Aurora data. So here, things to pay attention to is this red line. That's going to tell you if that IMF, the interplanetary magnetic field, is facing northward or southward. So if this red line is above 0, we don't care. If it's below 0, though, that's when we start saying, hey, maybe we should go and look at that camera and see if there's some Aurora out. Other things to note is the density. We like to see high densities, so usually above 10 here on this scale is a good density to have. That means there's a lot of stuff in the solar wind that'll come down and interact with our ionosphere. And also the wind speed. So the solar wind speed right now, you can see it's 500, maybe a little higher, a little lower. But that, if it gets super high wind speeds, that's when we can start seeing possibly those red and blue Aurora colors, which are always pretty neat. Another site here is just our GI Aurora Forecast website. This also has a lot of good information if you want to just learn more about the Aurora or forecasting the Aurora. Here we can see the KP values for our forecast for 27 days. And the 27 days is based on the sun cycle. So the sun takes 27 days to spin around. So typically, if we see something interesting, it might come back in 27 days. And that's what that's based on. So you can see we have a couple interesting days coming up. We just had some nice ones that we talked about before this back on the weekend. And we got a few more coming up on the 28th, 29th, and 30th. So definitely pay attention to our Allsky cameras on those days if you're interested. And even on these, you know, smaller KP value days, sometimes we can see Aurora if we're lucky. So with that, I think that is all I've really got for you guys. Unless you have any questions.
Yeah, I have some comments / questions. You were saying that really an Aurora is 2 events. There's one in the northern hemisphere and one down in the southern hemisphere. And this happens simultaneously. Is that correct?
Yeah. So
this means if you were able, you could see Aurora in the north, and if you're down in the southern hemisphere, you could also see it there.
Yep.
But I assume that doesn't really happen, because if it's daytime in the southern hemisphere, it'll be nighttime up towards the North Pole, and so the southern people can't see it. Northern people can.
Yes, yeah. But there's this ideal window on the equinox where we have kind of even days and nights in the northern and southern hemisphere. Because obviously up here in the winter we have much longer nights, and during that time in the southern hemisphere they have much longer days. But if you get on that cusp period in between summer and winter, and you get right on the edge of day-night, then sometimes you can get alignment to where, and it's been done a few times, there are images online where you can see conjugate aurora, where there's 2 cameras, one in the north, one in the south, and they actually do show the almost identical auroral patterns in the sky. And it's so cool to see. I should have included a few of those, but definitely Google image that and it should come up. Conjugate aurora. It's very neat.
I suppose they wouldn't look exactly alike or exactly opposite because of our own planet's atmospheric wind speed carrying this stuff around.
It's actually surprisingly similar though. So up at the altitudes of the aurora, Earth's atmosphere doesn't have much effect. So the wind speeds are influenced by the magnetic field and the solar wind more at those altitudes. And the solar wind's uniform across, well, uniform enough that these magnetic field lines, they're going to match on the north and south. And then those particles, because the reconnection event's happening here, the particles just split right in half and send along the same magnetic field lines back to Earth.
Okay. That I think that's very fascinating.
It is.
I never realized that what happens up north happens down south and vice versa. That's something new to me. You were talking about some charged particles in the solar wind. What are these particles? Yeah, I know you're talking about, you had some electrons.
Yep, it's usually, so in plasmas, it's usually electrons and protons that are floating around on their own. We can distinguish between electron aurora and proton aurora. Proton aurora are generally, you're gonna test my knowledge. I think they're more equatorward than electron aurora, but the electron aurora are more common. So you can get interactions. They do separate a little bit. That's not something I'm too perfected on, but it's a mixture of both particles, but the ones that we generally see and can indicate as our normal aurora are caused from electrons.
Mm-hmm. Okay. Do you mind if I take you off screen share for the moment?
Yeah, I can stop sharing.
Oh, okay.
There you go.
Of our studio audience here, does anybody else have a question?
I have a question.
Sure.
And I'd like to ask a question on behalf of those who are watching who are completely inexperienced. And I'm the perfect person to be asking on behalf of the inexperienced. I live in Florida. And so I understand that, there are some projections of the northern lights and when they'll appear. But generally speaking, is there a time of year that a Floridian or someone in my kind of latitude would say, well, I'm going to be planning a trip this time of year, hoping it'll be active? And how far north does one have to go, remembering that, the cold is awfully cold to a Floridian?
Yeah.
Go ahead and laugh, John.
No.
But I guarantee you, I'm asking a question that's on the minds of a lot of people watching this.
That's a very valid question. And there's multiple parts to it, of course. So instead of time of year, you actually want to think about what year you're going to travel. So the sun is on an 11-year cycle. Right. So there's solar maximum and solar minimum. So we just went through the most minimum solar minimum on record.
Absolutely
I think in 2019.
Boring from my point
so
of view.
Boring. So boring. So that was 2019. We're on an upswing. So in the next several years, it should get better and better. It's definitely, we've seen more and more aurora this year than last year, which has been great. So if you're looking to travel, the next couple of years, your time to go. If you wait too long, we're going to get to another solar minimum and it's going to be boring. But time of year, usually there's less cloud cover in winter just because the cold weather prevents, the rain and all those weird things going on that you summer people have. But especially around the equinox, so September and March. And the reason that is because Earth is traveling around, if this is the sun, Earth is traveling around the sun on a tilt. So the best time, eventually the magnetic field orientation of the sun aligns perfectly with that tilt, and that is on the equinox. So March equinox and September, what is that, September equinox? Yeah, but we usually do the March one. That's when we do our rocket missions and everything, because we have the most active aurora there and it's colder, so that we have better chances of clear skies to see the rocket launches and stuff. As for how far north you have to go, that's up to you. So if it's a really good year and a really good aurora storm, you can see it in, the lower 48 northern states. If you get crazy, they have seen Aurora in Cuba, so you could see it at home. But if that happens, we'll blow up the grid system, which would be, interesting, and it could be pretty bad. So we're hoping to not see one of those, I guess. There was an event a couple of years ago, it might have been 2017, where we had this CME that was big enough that it was coming, if it was coming towards Earth, it would blow up our grid. However, it went in a different direction, and one of my advisors went, darn. And it was just like, wait a minute. So that was pretty funny.
Well, those are great answers, and they're very helpful to me. I will say that I have seen the Northern Lights one time in my life when I was living in the St. Simons Island area of Georgia, which almost is in Florida, and just visible for a few seconds. And that was pre-internet age, when we didn't worry so much about the electronics as we do today.
Yeah,
I think that was probably the 80s and 90s.
Yeah, and there was one around that time that they have images. If you look online, you can see transformers that blew up just because of auroral activity, just because there's too much going on in the atmosphere, and our electrical systems can't handle it. I will say, if you do plan on traveling, especially if you're traveling to Alaska, realize that in the summer, you are not going to see Aurora here because we don't have night. So keep that in mind, because some people do come here in summer, and I do give these auroral talks in summer, and they're like, when can we see Aurora? And it's like, well, you'll see the sun. That's as close as you're gonna get. You can watch the sun go like this all night.
Okay.
So keep that in mind too. Look at the nighttime phases and make sure you have night to wherever you're going, because that is important.
Good point.
Yes. Yeah. And that's the better thing about winter too, is if you travel in winter, there's more night, which means more chances of something happening.
I've got what? Oh, I'm sorry.
Oh, Terry, go ahead.
Okay. I was lucky enough to be in Alaska when they had open house at Poker Flat.
Oh yeah, that's fun.
It was amazing. And I got to stand there and watch LiDAR run and take pictures. Now, I've also been on Clary Summit when I could see LiDAR running. I didn't know when I was on Clary Summit, I was thinking it was some kind of adaptive optics or something.
Yeah.
Actually going down and seeing it, I knew they were measuring something in the atmosphere. And so from your talk, could you talk just a little bit more about what LiDAR does?
Yeah, so LiDAR, they are shooting light into the atmosphere, and they're waiting for the reflections off of things in the atmosphere. So they can tune it in different ways. They can do bouncing off particles in the same way that my instruments do measuring the color changes. So they can have it fast enough that they can get wind speeds from that. They're not very accurate, if you ask me. They can also get densities. So you can see how dense an area is with where you're pointing the LiDAR beam, and see how many reflections you're getting and the difference in speed between the reflections to see what levels have more or less reflections and stuff like that. They do use it for cloud cover, because if your clouds are at a low enough altitude, then they're blocking whatever you want to see at the higher altitudes. But if you do have clouds and they're high enough, you can still see whatever you want to see. So they measure altitudes of clouds and stuff like that. LiDAR runs, I think, quite often. I'm not sure if it's every day, but there's people out there all the time running that thing. And it's really cool. It's cool that you got to see it, because a lot of people don't realize that you can see that green beam. It's not just in photos. There is a little spaceship beam going up into space out there. It's really sweet to see.
Because I was shooting the Aurora, and I could see it going up there. And I was, like I said, on Clary Summit, and I was talking to the guy next to me, and I said, what is that? I see a laser looking thing up there. And he explained, it was LiDAR, but to actually be at Poker Flats to see this, do you think
big it is?
Another chance that they will do another open house there?
Yeah, so They actually do walking tours every summer. It's the first and second Thursday of the month, or the first and third Thursday of every month. So they do open it up quite a bit. We had an open house. Was it the one in 2019 that you went to?
Yes. Yeah, I was.
Yeah.
Yeah.
Yeah. It was packed.
Yeah.
So the open house in 2019 was somewhat a disaster from our end, but that's okay. It was just, we didn't realize how many people would be so interested in that range, and we were not prepared for the number of people that showed up. But it was great to see all the support from the community. So I think that they will do it again once they're better equipped. Also, 2019 was an interesting year. We didn't have any rocket launches out of Poker Flat. We were shut down for modifying buildings and updating facilities and stuff like that. So that was another reason where they were like, hey, no one's going to come out here. Let's invite everyone out here. So hopefully we'll get another chance like that. I think they'll take some time to recover from the last one, but I hope they do it again as well.
Me too. You brought up rocket launches. You've got 3 scheduled for December of this year. Any chance you might go on to March of next year?
It's possible. There's probably some that will get scheduled in March. Everything's getting a little weird with NASA because of COVID. So I was supposed to be on a rocket launch in Norway in 2020 or November 2020, which is now happening November 2021. And then some of the other rocket launches, like everything's getting pushed around. And since NASA has to send crews out to these different sites, even something that's happening in Norway can affect something that happens at Poker Flat, which can affect something that happens at Wallops. It's a big mess. So everything's still getting figured out. Hopefully there's something happening in March. And if that does occur, then definitely check in on Poker Flat's social medias, because we do live streams during the launches. We try and keep people updated so that they can go out to Chattanooga Lodge or Cleary Summit and you can actually see the rocket launch. And we'll try and keep you updated with times and when we think it's going to launch and all that kind of stuff.
Thank you. I really enjoyed your talk too. That was amazing.
Thank you.
Well, yeah, thank you, Kylie. I'd like to conclude here by introducing everybody who's on our studio. First, I'll start out with Kylee Branning, who's from the University of Alaska. She was our speaker talking about Aurora and her experiences with it, both visually and through the science of Aurora. Terry Mann is the current secretary of the Astronomical League. Maynard Pittendray is the current executive secretary of the Astronomical League. And my name is John Goss. I'm former president of the league. But thank you all for tuning in. And thank you, Kylie, for giving us this very fascinating. I was taking notes, by the way. I was taking notes. But
well, if you have any questions after this, feel free to email me too.
And we had some difficulty in arranging this because there are time differences. I'm on the East Coast. She's in Alaska. Well, we got to pick a time that's suitable for everybody here. But I appreciate you taking your time in doing this. So unless anybody else has any questions, we'll sign off and we'll see you all again sometime.
Thank you.
All righty.